I've updated the next couple of weeks. Actually, I think into July. So for the next couple of weeks, I'll update the rest of the syllabus by this weekend. But for the next couple of weeks, these links should be accurate. We're going to start tonight with an introduction, which is chapter 1. Some point. Oh, you're right. And 7-6 should be 7-5. Okay, I'll fix those dates. Yes, you're right. It should be 7-3 and 7-5. It's taking a while to download. Let me see if I can bring it straight up from my website. Now I'm just going to open it. Okay, I thought I saved these as PDFs. Sorry about that. I'll update them and save them as PDFs. Let me see. It doesn't let me. It's only going to let me read it. Okay. So I thought I saved these and uploaded these as PDFs. So sorry about that. I will, so that you don't need PowerPoint. I will do that and get that uploaded. But let's give it a start. So basically, might go through this chapter fairly quickly because this thing covers a lot of basics about computers and how operating systems work and stuff like that, and stuff that probably most of you already know. And then it does get into writing some Java programming, some of the history, how to do a graphical output. Some simple examples tonight. So again, this basically gives you sort of the basic makeup of any type of computer, with a storage device being your hard drive, the memory, which is the physical memory. So a lot of times you buy a computer, it might say it's got 500 gigabyte of disk drive. That's storage, and maybe it has 4 gig, or some computers have 8 gig of memory. That's what we used to call the RAM, or the random access memory. So that's the memory. And the CPU, that's the thing that Intel makes. And communication devices such as modem. NIC is a network interface card. That's what you plug that sort of thickish phone cable sort of thing in. Obviously, the keyboard and mouse would be for input and for output devices. So nothing really complicated there. The CPU is really the brain of the computer. It retrieves instructions from memory and executes them. The CPU speed is measured in megahertz, with 1 megahertz equaling 1 million pulses per second. So now most computers today are probably an Intel Core Duo is, 2.5 megahertz. So it's quite fast. So it's really fast when you think about 1 megahertz equaling 1 million pulses per second. So a typical computer at 3 gigahertz is billions, like 3 billion of instructions per second. So these things are really fast. Memory is where the memory is stored. And memory is stored in something called bytes. Each byte holds 8 bits. And so I don't know if everyone is familiar with bits and bytes terminology, but we'll cover that a little bit tonight. So that's what the memory is. And it used to be that 8 bits makes up 1 byte, and 1 byte makes up 1 character, like the letter A or B or something like that. That's not really it's not necessarily the case anymore. So, because of expanded character sets. Okay, here we go, the bits and bytes. So, each one of these lines here is essentially a byte. You see as zeros and ones. Each one of the zeros and ones is a bit. And the way it works is it adds up. So these things will add up to a particular number. So let's see. I've got another handout. Let me see if I can get to it. It's binary. So let me move to this binary example for a moment, which is there as well, and then we'll go back to the slides. Because I show you how these bits work here, and I'm not sure they're going to show it to you on the slides. But each one of these bit locations, starting at the far right, it's either a 0 or 1, meaning it's either on or off, which means it's like a light switch. The light is either turned on or it's turned off. If it's turned on, then it's a number. If it's turned off, it's 0. And those numbers increment, they essentially double every time you move to the next place. So it goes 1, 2, 4, 8, 16, 32, 64, 128. Now, if you add them all up, you get 255, which is the maximum amount of characters you can have. So the maximum number of combinations you can have, essentially. So, for example, the letter A is represented by this series of bits. And if we go back to, we'll look at it in a moment. Let's see. Okay, so here we have the letter J is 0, 1, 0, 0, 0, 1, 0, 1, 0. So if we were to add this up, this would be 0. That would be 2. That would be 8. So 10. Let's see, 16, 32, that's 64. So that's 64 plus 8 is 72, plus another 2 is 74. So it's saying the uppercase letter J is 74. So if A is 65, because I showed you in that example, you just keep adding it. So A, B, C, D, E, F, G, H, I, J is 9 from A. So 9 plus 65 is 74. So, and if you looked at these numbers, that would add up to 74. Lowercase a actually has a different value than uppercase a. It's actually, the uppercase letters are always 32 more than the lowercase letters. And we could look at those numbers and add them up. We'd see it's 97, by the way, for A. But if we were to add it up, it would be 64 and 32 is 96, plus 1 is 97. And if you subtract 65 from that for uppercase A, you get 65. You get 32. So all uppercase letters are exactly 32 numerically less than the lowercase letters. And if you were to look at all these encodings, you would see the same thing. Numbers are strictly numeric. So if you look under 2004 for this number here, 11, that's in the second position, 1 means 2. 1 being on means 2. And in the first position, 1 being on means 1. So if you add 2 and 1, you get 3. That's how you get it. So if we were to go back to this here, I pretty much show you the same thing. I say that 1 is the number 1, and then 1 is the number 1. And then in binary math, to add them up, you would simply add these two up, but because they go to the top value being 1, in binary means 1 and 2, so that goes to 0, and we literally carry the 1, and then that's how we get the 1 down there, and the actual value in decimal is 2. So this is kind of how it works. By the way, binary 8 bits to a byte equals 1 character is an old way of doing it. The new way of doing it is to use something called Unicode. And that's because 255 is enough to cover the entire Latin character set, which includes basically Western Europe. But it's not enough to cover all the Chinese letters and Arabic letters and things like that. So they essentially doubled it to Unicode, which is 2 bytes equals 1 character. So when we double this, it increases exponentially. So if our top number here is 128, then when we continue it, it's 256, 512, double, 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 32K, add them all up, and you get around 64,000. It's actually 65,000 and change. And now you've got 65,000 unique combinations of characters that can be used, which right now is enough to cover the entire character set.